This is the third video on integrated rate laws in kinetics. So we're looking at changes in concentrations with time. And that's the kind of data you're going to get when you're looking for integrated rate laws. So with integrated rate laws, you're looking at concentration and time data, and it's going to be analyzed graphically. So we're going to be looking at linear relationships between concentration and time data. And that's going to help you determine the order of the reactant. If it's a zero order reactant, the linear relationship on a graph is going to be concentration versus time. So you're going to have a linear relationship in concentration versus time. If it's a first order reactant, the linear relationship on the graph is going to be the natural log of concentration versus time. So we're looking for a graph of natural log of concentration versus time that's going to have a straight line. If the reactant is a second order reactant, then the linear relationship on the graph is going to be the inverse of concentration versus time. So these types of questions, you're going to get 2 or possibly even 3 graphs will be presented, and the graph with the straight line, the one with the linear relationship, will be the graph that determines the order. It's your job to recognize the straight line and know the graph to order relationship. So you got to start memorizing and remembering which graphs are which. So start learning them now. Which ones are the connections. So zero order is concentration versus time. First order is the natural log of concentration versus time. And second order is 1 over concentration versus time. Gotta learn them. All right. This slide has a really good representation. Look at the real PowerPoint. It gets a little messed up on the videos. But there's your 3 graphs. So zero order, concentration versus time. First order, the natural log of concentration versus time. Second order, the inverse of concentration versus time. You're looking for the straight line. All right. And then once you know which is the graph with the straight line and the correct slope, then you know the order. Once you have that, you know the equation for the line. And if you know the equation for the line, then you can use that equation to find any point along the line. The 2 equations on the AP equation sheet are the equations for the first order and the second order lines. This one and this one. They are not in slope-intercept form, so just be aware of it. All right, so how are we going to get this presented to us? They're going to give us graphs, and we're going to have to recognize the graph, and we're going to have to look at the graph and determine the order. So here's an example. It says the following data is obtained for the gas phase decomposition of nitrogen. So here's the reaction, and it's asking us, is this a first order or a second order? And then therefore write the rate law. So it's pretty straightforward. Looking at the 2 graphs, we're looking for which graph has the straight line with the correct slope. So this is the graph with a straight line. And therefore, which graph is this? It's 1 over concentration And which graph is that? Second order. So write the rate law since it's second order. Rate is equal to K in O2 to the 2. Simple as that. Recognize the graph, find the straight line, know which order it is, write the rate law. Have a data table. And since we have a data table, can we find slope? We have some data. Take 2 points. We know it's a straight line. If we take the inverses, we can find the slope. Okay? So pick 2 points on the data table and let's find the slope. All right? We could pick this point and this point. And the time, the total time, the 300 seconds, and we can find the slope from there. Okay? Then once we have that, there you go. Data. We can, how are we going to use this? Once we know which graphs are which, then we're going to have to use the equations for that line. So here's the equation for the first order line. All right, these are on your equation sheet. This is the first order line. This is the second order line. Note that they are not in slope-intercept form. So this is the concentration initially, A0. This is the concentration at any future point along the line. That's your y's. So that's your y-intercept. This is t, which is your x, and negative k. Yep, that's little k. That's your rate constant. That's your slope. All right. So what do we have here? We have, whoops, let me erase that. All right, second line is your second order, same idea. There's your y-intercept. Y-intercept, any point along any y, x, there's your slope, k. All right. This doesn't look written correctly, so I'm going to rewrite it real quick. You're also given a half-life equation for your first order reactant. T1 half is equal to 0.693 little k. Why do they give you this half-life equation for first order reactants? Nuclear decay is a first order, and if you know the slope of the line, or little k, you can calculate the half-life for a nuclear reaction. All right, it's just a quick and easy way to calculate half-life. So if they ever ask you to, if you've done a reaction or you've calculated a little k and then they ask you to calculate the half-life, use that equation. Quick, we can use this equation for the line, and then we can answer the second part of the question. So for this problem, we're going to look at the decomposition of nitrogen dioxide that we already looked at the graphs for, and calculate the little k, and then use the information from the graph to use the equation for the line and look at the concentration and the time and figure out what the concentration will be at a future time point. So it says, what's the value of the K And then what is the concentration at a future time point? So first let's calculate the value of K. Remember that the K is going to be related to the slope of the line in the graph, the straight line graph. So all you have to do is calculate the slope. So it's just rise over run. So little k is going to end up being, just pick some points from the data and do rise over run. So I'm just going to pick the initial point and the final point. Remember that our graph is the inverse graph, so we're going to say k is 1 over the initial concentration minus 1 over, and I'm just going to go all the way to the final concentration, divided by the initial time and the final time. And when we calculate that out, plug all that into your calculator, you end up getting a K of 0.544, ends up being our K. Now, what are we going to do with this K? Well, we're going to use this K to plug into the equation for our line. I'm going to go ahead and put the units of our K on there. Now remember that the graph that we picked was the inverse of the concentration versus time. So for that graph, the equation from our equation sheet is 1 over concentration at time t minus 1 over the initial concentration is equal to little k times t. So if the initial concentration is 0.5 molar, the question is, what will the concentration be after a half an hour? So what are the two things that they're telling us? They're telling us that we know the initial concentration, so we can plug that in here. We know the time, we can plug that in here. And we just calculated little k. If we know those three things, we are going to be able to find the concentration after a half an hour. Now watch out, because this is a little tricky, because they gave us our time in hours, and we're going to have to change that to seconds because our little k is in seconds. So we're going to have to do a little bit of converting and a little bit of plugging and chugging. So what do we know? We don't know our initial concentration, so I'm just going to say 1 over our we don't know our final concentration at time t, but we do know our little k, and we know our time, and we do know our 1 over our initial concentration. So let's plug what we know in. We know our k is 0.54. We know our time is a half an hour. Change that to seconds. That's 1,800 seconds. And we know our initial concentration was 0.5 molar. Now if we calculate all of that out in our calculator, we get 9.794 times 10 to the 2. And remember that all of that is equal to 1 over the final concentration. So to take that and get the final concentration, we just need to get the inverse of that. So the final concentration after a half an hour is 1.02 times 10 to the negative 3 molar. That's the final concentration after half an hour. So we've used the equation for the line, and that allowed us to find the final concentration of the nitrogen dioxide after a half an hour. It decreased because it was a half a molar, and now it's 0.001 molar. Hope that was helpful.